This video contains the solution for the Physics C Mechanics Free Response question number 3 from 2008. We have, let's see, in an experiment to determine the spring constant of an elastic cord of length 0.6 meters, the student hangs the cord from a rod as represented above and then attaches a variety of weights to the cord. For each weight, the student allows the weight to hang in equilibrium and then measures the entire length of the cord, much as you did when you measured the spring constant of the slinky in your bungee jumper lab. The data are recorded in the table below. Use the data to plot a graph of weight versus the length below and sketch best fit straight line. They have it all scaled. You could not possibly blow this, I think. These are points being given away. We'll take them. So let's see, let me just get the equation here. Get the points put in. Go to Stat, Edit, clear out my list. Remember, don't do delete, just do clear. And we have on the x-axis, I guess you could, the possible mistake you could make here is when you're doing your best fit line, this is the x-axis, so these should be first 0.6, 0.97, 1.24, 1.37, and 1.64. And then on the y-axis, we have weight of 0, 10, 15, 20, and 25. Those are already in newtons. Go to Stat, calculate line of best fit, and according to that line of best fit, which is from the calculator, we have y is equal to 24.1 x minus 14. That's what you call that. Maybe we call that 24. And we're looking for, this is force equals kx, so this is the spring constant, right? We need to recognize that this is force equals negative kx. Now, why did that not come out to be negative, you might wonder? Well, the reason is they did not take into account that the length and the force, in other words the weight, are opposite directions. The spring force is actually opposite to the weight, so we're just using magnitudes here. So our k is equal to 24, and the units, well, it was the slope of this, so newtons per meter. And you remember, those are the correct units for a spring constant. Now, part C, let's see, the student now attaches an object of unknown mass, very much like your bungee jumper, to the cord and holds the object adjacent to the point at which the top of the cord is tied to the rod as represented above. When the object is released from rest, it falls 1.5 meters before stopping and turning around. And we're neglecting air resistance. So calculate the value of the unknown mass m of the object. Well, let's see. Energy considerations here. The object is falling 1.5 meters. And from here to here, at the top, it's not moving. The object, all of its energy, up here at the top, that's all potential energy, gravitational potential energy, that is. That is mg times 1.5, right? mgh. And the energy at the bottom, it has no gravitational potential energy, and it has no kinetic energy either, because that's how far it dropped just when the spring was stretched all the way and it started to turn around and go back up. So the energy at the bottom is all spring potential energy. That's the only kind it has. It's lost all 1.5 of its potential energy. It's stopped, so it has no kinetic energy, so it only has this. So if we want to calculate the value of the unknown mass, these two things, its initial energy must be equal to its final energy, because we only have conservative forces, gravity and spring, acting on this, no friction or air resistance. So mg times 1.5 must be equal to 1/2 k, which is 24 from our last part, times x. Now I got to think about what this x would be here. That's how far the spring has been stretched. And remember from the first part that the spring is, its slack length is 0.6. So it doesn't get stretched at all until we stretch it from 0.6, right? With no weight on it at all, it's still hanging down at 0.6, just like the slinky in your bungee jumper lab hung down a certain distance. So before it was stretched at all, we had to subtract that distance out. So the 0.6 doesn't count in terms of how far it got stretched. So it didn't start getting stretched until 0.6, so the remaining 0.9, that's our x here. That's a very important consideration here. And then solving for m here, let's see. We have m is equal to 1/2 times 24 times 0.9 squared divided by 1.5 times g, which is 9.8, which gives us about 0.66 kilograms. Just check that calculation, make sure that that looks right. So mgh is equal to 1/2 k x squared, and that gives us 0.66 kilograms. All right, the last part, part D. Calculate how far down the object has fallen at the moment it attains its maximum speed. Well, let's think about that for a minute. Its maximum speed. Speed or velocity will reach a maximum when its derivative is 0, and the derivative of that is acceleration. So max speed happens when acceleration is equal to 0. And as a consequence of Newton's second law, acceleration is equal to 0 when net force is equal to 0. So what forces are acting on the mass? There are two forces acting on the mass: gravity and the spring force, which is kx. Not 1/2 kx squared, that's the energy, right? That's the potential energy of the spring. The spring force is actually just kx. So the net force will be 0 when those two are equal to each other. So let's see. K is 24. X equals the mass, 0.66 times 9.8. And that gives us an x of 0.66 times 9.8 divided by 24. That is about 27 centimeters, or 0.27 meters. Now, that, we need to make a little adjustment to that, because that's how far it's fallen. When it's in free fall, it's just accelerating, and it doesn't start decelerating I should say the acceleration doesn't start decreasing until the spring starts to stretch. So it's this 0.27 is the x, and just like our consideration here, the x distances happen from the 0.6, right? So really, where does it happen? It happens after it has fallen the 0.6 meters plus stretching that far, so at 0.87 meters. Right, because this is all free fall, it's definitely speeding up here. And then the acceleration decreases, and right here the acceleration is 0, and then after this point the acceleration is upward. The kx starts to dominate, and we actually have upward acceleration, which slows it down. That was part 1 of D. Part 2, explain why this is the point at which the object has its maximum speed. Well, we've kind of done that in the discussion here. We could say something like, because net force is 0 and acceleration goes from downward, I was going to say positive, and we're treating the positive direction like it's down here, so from down to up. So something like that. And last, they want us to calculate the maximum speed of the object. And these, we need some energy considerations here to do that. So let's see, we want its velocity, maximum velocity. Well, we know where that happens, so we just have to figure out what's going on energy-wise at that point. So 1/2 mv max squared, that's kinetic energy. Well, at the point where it's fallen this far, what's happened energy-wise? Well, we've fallen this far, so we have mg h worth of potential energy that has been converted into potential energy, right? But as we fall down this way, there's also some energy from the spring that is being converted into kinetic energy, and that is 1/2 kx. And let's see, how much of x do we have? That's the same x that we had here, right? That's the amount that we stretched, not the 0.87, but the 0.27 that we stretched there. So again, if you were wondering why this wasn't a minus, let's think about this for a minute. As the ball drops from rest down to the point here, 0.87 meters down, we know that that's where it reaches the maximum velocity. Now we're trying to figure out what that maximum velocity is. Well, at that point, it has lost, it has given up this much potential energy of the gravitational type and given up this much gravity, or its potential energy, sorry, of the elastic type. So these two types, these two energies have been transformed into kinetic energy. And let's see if we can solve that now. So we know what the mass is, it's 0.66. So Vmax is equal to the square root of, let's see, multiply everything by 2 here. 2 times the mass times 9.8 times 0.87. Plus we multiplied this all by 2, so that 1/2 is gone. 24 times 0.27 squared, all divided by the mass, 0.66. Let's see if I can jam that all into the calculator. So let's see, we've got the square root of, and I want that whole top of the fraction in parentheses, so another set, open there, 2 times 0.66 times 9.8 times 0.87 plus 24 times 0.27 squared, close parentheses, that closes the top of the fraction, divided by 0.66, and that closes the square root, and that gives me 4.43, which is not the correct answer. So let's just check here and make sure we have the right numbers here. I think we're looking for about 3.8, if I remember right. So multiply both sides by 2 and put a 2 there. The mass is 0.66 GH plus, multiplying the 2 over here, cancel that out, 24.27 squared divided by the mass, and we have the square root of that whole thing. So this is the right idea. We're not getting the right answer. I think we're supposed to get about 3.8, so I'll have to get back to you on that. To be continued. Calculate the maximum speed. According to this, we got 4.4 meters per second, but that is not agreeing with what I believe the correct answer is supposed to be. So we must have made some kind of small error. We have kinetic energy, 1/2 mv squared, is equal to the amount of energy that has been given up to kinetic energy at that point. So we'll have to come back to that.